The topic of this video will be hopping conductance in organic semiconductors. So as a bit of background, when we consider an inorganic semiconductor like silicon, we consider a sea of electrons around a positive ion core. And as we add to the sample, we could imagine this cloud just getting bigger and carriers can freely flow throughout our sample. Now, when we have organic compounds, we can imagine each molecule has its own delocalized pi system where electrons can freely flow. But as we add to the sample, we add additional molecules. And we can imagine electrons could exist in the pi system of each molecule. But we obviously want carriers to be able to flow through the entire sample. So we can imagine we would have to pull an electron from here and put it in this pi system. And that would come with some sort of energy cost to make that happen. As is the case with many aspects of organic semiconductors, we have to consider the physical arrangement of the molecules. So if we have a very regular structure with well-defined intermolecular spacing and orientation like pi-pi stacking or a herringbone structure, we can imagine carriers very easily flowing up or down the stack. Now, if we have an organic compound in solution, we can imagine all these molecules might be very oddly spaced. They could all have different orientations. So it could be very difficult to get a carrier from one molecule to another. Now, the way we describe this graphically is kind of this periodic graph where we have the energy of the carrier along one dimension of our sample. So we can imagine when the carrier is in the pi system of any single molecule, it would be at its lowest energy state. So we would be in the troughs here. But to be able to move between them, the carrier would have to exist in some space outside of the orbital. So we can imagine it's not very happy with that. So it would have a very high energy. So we would have to move it over this hump. Now these two curves just show the disordered or ordered case, where if we physically bring the molecules closer together in a more regular arrangement, we just lower the height of the peaks or the activation energy to transfer the carrier. So we usually describe this as some sort of quantum probability where we can imagine the carrier existing in a trough and it's going to bounce around that trough, and eventually it may happen to have enough energy to overcome this peak and end up in the next trough. And that's how we get electron transfer. The way we mathematically describe it is with an exponential. Up here, we just have how difficult it is to move that carrier, and that's activation energy. And on the bottom, we have temperature, because we can imagine as we add thermal energy, those carriers are going to move around more. They may have more energy to begin with, so it might actually be easier to overcome this peak and end up in the next trough. So empirically, what we see in samples exhibiting hopping conductance is an increase in mobility with an increase in temperature because you are giving those carriers more thermal energy to make that jump and overcome the barrier. Now, there are other samples where the behavior might be completely different. The mobility might decrease with temperature and may be more complex. So it's important to make this distinction and characterize our samples in this way. And obviously the whole point of semiconductors is we want to know how we can move charge through them to accomplish some goal. So understanding the physical mechanism by which that occurs is very insightful and can help us plan for how our devices might function under different temperature conditions. So that is all. Thank you.